Thank you for the opportunity to present. My name is Chris Orban, and I'm a professor at Ohio State University in the high energy density physics group that's there. And I also collaborate closely with the extreme light group at Wright-Patterson Air Force Base. The work today is not connected to the Air Force, but before I start, I do want to give a shout out to some of the students and colleagues who are also presenting things. Professor Joe Snyder from University of Miami, postdoc Joe Smith, who got his PhD this year working with me, and then two undergrads who are looking for grad schools, so I encourage you to check out their talks if you have a chance. So I was one of the first academic users of the Flash code after added to it was high energy density physics extensions. So this was back in 2011, 2012. And the Flash code was originally designed to do supernova and astrophysical type things. And then added to it was things like laser refraction, equation of state, tabulated equation of state, those sorts of things. And so at the time in 2011, 2012, it wasn't entirely clear whether it was going to line up with predictions of the Hydra code, which had been extensively used. So what I chose to do at the time was look at this paper, Grave et al., which is from the Colorado State group, which is an excellent paper. Nobody from Colorado State pays me to say that, but they did a very good job. And they have very nice interferometric measurements of an expanding target because of nanosecond laser radiation. And so I'll talk about that in a moment. But as we were considering this problem, we started to think about astrophysical jets and how do you create an astrophysical jet in a laboratory. And so the project kind of took a direction at that point as well. So here are the basic results from the study. So this is from these two panels are from Grave et al. So this is previously published Hydra simulation, so I didn't get any sort of inside information in that sense. And this is soft X-ray interferometry of an aluminum V-shaped groove that's sort of coming out of the page here. And it's not a laser spot that's irradiating it. Instead, it's a line focus, sort of focusing on this whole thing. And what happens is that this aluminum gets heated up, and it expands here, and it collides in the middle, so it becomes much denser. And in fact, it's so dense here that it's exceeding the density that the interferometry can probe. And so it's dense, and it's hot, and it expands over time, those sorts of things. And so there's some really nice Hydra simulations in Grave et al., which I believe were run by Mike Purvis. They published that overall looked pretty good over these different time scales. So I was the first person to publish these Flash simulations, which, not too surprising, lined up pretty well. Now, what makes this an interesting problem is that radiation effects are important. And so radiation effects go as z squared. And so for aluminum, that's pretty significant. And so in the experiment, the aluminum collides in the center and becomes dense and hot, but that heat can get radiated away. And so what that does is that allows this to cool, and this dense feature can stick around for a longer time because the pressure is lower because it's cooled. And so what's interesting is that you can do simulations without radiation, and this is the previously published Hydra simulations without radiation, and see what happens, and the aluminum collides in the center. It's hot and dense, but it cannot radiate that heat away. And so as a result, this feature does not stick around for nearly as long. And so it kind of expands like this over time. And so it's nice to see the codes agreeing, but this is ultimately the physics of what's going on. So you can do things like, quantitatively compare the width of these jets, things like that. You can look at the temperatures and the ionization states. In general, it's a tricky problem to figure out exactly which equation of state to use, and I was often using Propacius equation of state. That worked pretty well for me. You can compare the ionization states as well. One interesting thing I found in doing this project is that Hydra has the capability to have negative electron pressures, whereas Flash does not. So instead, with Flash, whenever I had negative electron pressures from Propacius, I would just set those pressures to 0. And so for Hydra, you have an ion pressure and electron pressure, and those two things can add together to give you basically 0 pressure. if it's something rigid and solid like aluminum. But in flash, I wasn't able to do that. I could only try to reduce that pressure by setting the electron pressure to 0 if it was negative. And so as a result, you see this kind of difference here. Now, in this study, in what I did, it seemed not to make a difference, but one can imagine other situations where it would. So at the end of the day, if you're shooting things with lots of energy with nanosecond lasers, it's probably okay. But as that energy gets lower and lower and lower and lower, eventually you might expect this to make a difference. So the second part of the study was thinking about the physics of this result and thinking about what you're really trying to do in terms of making astrophysical jets. What would be an ideal astrophysical jet if you could make one in the laboratory? So think of a tube of toothpaste. You squeeze the tube of toothpaste and it squirts off this way. How do you diagnose that? How do you think about that? Well, what you can do is you can think about the kinetic energy compared to the internal energy, where the internal energy is basically the energy in heat, you could say. And for an astrophysical jet, think of a quasar squirting a jet into the intergalactic medium. By the way, my background's in astrophysics, so this is part of why I like this problem. But if that's happening, then this jet is going into a medium that's cold, that's mostly stationary, and this jet is going to have a very high ratio of kinetic energy to internal energy, right? And so if you plot this on a plot of specific kinetic energy divided by specific internal energy, you're going to find things that are much greater than 1 for your ideal astrophysical jets. And as we were talking about the results with Don Lamb, who's a great astrophysicist, he pointed out, he wanted me to plot up what this looked like. And what's interesting is that part of why people got interested in this V-shaped groove experiment is because it creates this kind of astrophysical jet in the middle. We saw that with the interferometry data. So that's part of the motivation for doing this. But the question is, compared to an ideal astrophysical jet, what does it look like? Well, it turns out that there's a lot of structure here in terms of the ratio of the kinetic energy to the specific internal energy. And so according to these results, this is not such an ideal stand-in for what an astrophysical jet you would really expect it to look like if you have some high velocity thing going into some sort of medium. And we kind of tried to highlight that. And we also considered a related experiment from the NOVA laser, where they shot aluminum from 2 different angles and it collides in the middle. And we argued that this geometry had much more in common with this earlier geometry, which was used in a study called Wan et al. And again, you don't tend to find the kind of high ratio of specific kinetic energy to specific internal energy that you might hope for if you're trying to simulate trying to produce an astrophysical jet in the lab. That was kind of the upshot of the study. So that's what we found. Again, it was motivated to try to kind of validate some of the physics of the flash code, the laser physics, the tabulated equation of state, but also the radiation effects, which was added. And so flash seems to do an adequate job. So one last thing that I want to say that we learned from all this is that bear in mind that flash has this adaptive mesh refinement, so it's an Eulerian approach to simulating all this, whereas Hydra has this adaptive Lagrangian Eulerian approach that does allow the cells to kind of stretch with the flow. It's hard for us to tell without more information from the simulation, but it seems like flash is kind of resolving things more sharply than the Hydra simulations would. And this seems to have something to do with the fact that these cells are expanding because of the laser radiation, whereas flash just puts the resolution wherever it's needed. And so it's kind of easier to set up flash to make sure that the resolution is where it needs to be, and it's a little bit harder to twiddle this to the point where you get nice high resolution. But these kinds of comparisons can kind of hint at that. We don't really comment on this on the paper, but it does seem to be important to mention that flash is sort of more robust to plasmas that are expanding, for example. But thank you so much for your time, and I look forward to hearing your questions.